Okay, let's make a start. Welcome back, everyone. This is the second half of well, the PyTorch for ML course, and the aim today, well, the aim of the session is to get through the first notebook. I forgot to say that if you're feeling particularly keen, there are four exercises that we've created altogether. So if you battle through this, or you're finding it too easy, more than happy for you to make use of your time by buying another notebook to work through. So there's a few things to cover from last session that I forgot to mention. So first of all, I'll just check with everyone. Has anyone not installed the material, or is everyone happy with where they are in the material? Is there anything that I need to help with in terms of deployment or installation? It's okay to say that you're struggling, but and is the collab working well if anyone's doing that? Cool. Because I kind of glossed over it, but there are a few steps to installing. You have to create a virtual environment, pip install, and you should be good to go. Right, so I omitted a few things. Someone asked a really good question about class imbalance, and I covered that briefly at the end of the previous session, but we can actually just, maybe it's useful just to show you how to determine how many elements there are in each class, or how many penguins there are in each class. So the way to do that is to just or species on the pandas data frame and just do value counts there. And we can see that there's a slight class imbalance. Adderley is very well represented. Sorry if I'm butchering the names of these penguins species, but there's also Chinstrap has 68 examples, whereas Hadley has a little bit. So quite clearly there is a class imbalance, and that's why we're trying to be consistent in our evaluation. So our training set just takes most of those. We don't weight the training set in any way. We just take 80% of a random split, and then we evaluate on a very small subset, but we stratify the split. So we have 10 examples of one species, 10 examples of another, and we try to choose. We try to take 10 examples of male and 10 examples of female for each species. So we get 60 altogether. Okay. Are there any other questions on that? Cool. And finally, one other thing that I forgot to mention. I was kind of hinting at the start that we're prioritizing or using physical attributes of the penguin for our classification task. I forgot to mention that we also have island as a feature. So the island where the penguin comes from. Does anyone have an idea why that might be a good feature or a bad feature? And we could actually, by all means, include this in our model. We just convert instead of it doesn't have numerical values, or it does have numerical values, but we just have to convert those into a form that the neural network understands. So we could by all means use it, but does anyone have an idea why we wouldn't want to use island?
I suppose we get a really strong association between the island and the kind of penguins, and you'll never detect the one kind of penguin on an unexpected island when maybe you should. Yeah,
that's exactly right. Yeah. So it's definitely discriminative, but it's almost certainly a source of bias in the model, because penguins could be moved around. We're as I said, we're kind of relying on the physical attributes of the penguin over anything else. Okay, so and also just a reminder that last session we got as far as instantiating a dataset class, and the key thing to do here is to implement these length length magic methods and get item magic methods. We've been going on a lot about this so far, but what are magic methods? Maybe we didn't really introduce that very well, but magic methods are a way to define to enable your class or object, the instantiation of your class to behave in a certain way. So as a very simple example, if I open a Python interpreter and I want to just define something very simple, sorry if this is a bit insulting if people already know this, but
That's bigger.
sorry?
Bigger.
Oh yeah, sorry. So I defined a list of integers, and we might want to get, say, the length of that and an item from our list. So it all seems and if we actually look into a list object, we get a whole host of these magic methods that all do slightly different things or make the class or the instance of that class behave in a certain way. And it's all the same thing. It's what we're doing now with the dataset class. Okay.
Is help a magic method? I don't think you can do that.
Well, help isn't a magic. Is it help? I don't think so. Well, magic
or a dunder method.
A dunder, yeah, sorry. That is the other way of saying it. Yeah, dunder, double under. No, there isn't a double under help.
Sorry.
Sorry. Okay, so to put this in context, we defined our data set, we created an instance of that, and at the end of the last session, I said that there were some things that we could improve about this data set. We need to be able to return tensors, not just tuples of our pandas data frame. Did anyone have a go at that? Is anyone willing to? But it's okay because it's not all trivial. It's not obvious and stuff. So I can go through it if people want me to. And I'll probably make a mistake in doing so. So the whole idea here is just to, I think we might have already imported the relevant functions anyway, but no, I haven't. So I need to uncomment this line. This imports tensor and float32. I'm going to use those in the first task. So our feats, I'm just going to overwrite as tensor of that tuple, and I'm going to set the data type to float32. Does anyone know why I want to explicitly set the data type as float32?
If you've got any integers, and they won't, for example, if you've got labels, category labels,
Yeah.
they won't be treated nicely by the kind of neural network.
Yeah.
Tensor operations.
That's exactly right.
Yeah.
There's also another thing that probably catches people out is that most of the data type coming from a pandas data frame by default is float64. So we don't customarily typically need to train on 64-bit floats. It's a bit overkill. We can get good accuracy on float32. It's just unnecessary memory, and it probably won't train as quickly on GPUs which only support 32-bit floats. There are some other things to say about that, but we'll talk about it later. Well, the performance is likely to be a lot faster with float32 than 64. The floating point operations per second is much greater. The architecture units within the GPU which cater for floating point, single precision floating point rather than double precision. Okay, so the final thing is to convert the target. And it's pretty much the same thing. We take our targets. We have already defined this mapping between our species value, so gen2, genstrat, or adley. And it's just a case of using that. So what should I call it? Label map. No. I'm going to set the data type to long. And that's a class, dictionary, so to self. And import long. Is that clear before I move on? Don't worry about. I don't want this to be a basic typing exercise. So we do provide the solutions. So if you get stuck, ask me. We also have Isaac, who will be walking around if you need any help. We don't have to. That's a good question. We can just use hint. This is more of a demonstration of the fact that you can import these types if you want to. For this example, where we only have 3 classes, int will be fine. That's 32 bits. But
Can we put this as floater to as well?
that is a good question. I don't see why you would want to, because these are going to be used in a certain way in the loss function.
Yeah. So
you would expect this to be a certain form for that. In fact, I'm not sure how that will behave. You can have a play. Okay, so now we have everything as tensors. So we can iterate. Our data set is an iterable. So that means that we can iterate over it. And we will return features and target pairs. Sorry?
TGS typo.
Oh yeah. Thank you, Isaac.
Okay.
DGT. Oh yeah, TGS. Oops. So I'm terrible at typing, as you can probably tell. Follow me. You follow me character by character. I will probably make more mistakes. So okay, so that's now been modified, and we can use that directly in our training loop. Do people think that's a good solution? I've got these kind of hard-coded conversions to tensor. What might be the drawback of having things hard-coded like this in the class? I will show you another way of doing this. Like we have another implementation of this dataset class. I can find it. Which is a lot more general than what we've just done. So this is probably the more Pythonic or PyTorch-onic way of doing things. The reason why I left this out is it can be quite confusing. So don't worry if you don't understand all of this, but there's a reference implementation of this Penguin dataset class in the code itself, and we can use this. So the difference between this class and the one that I've got in the notebook is that we have to supply these X transforms and Y transforms. And these utilize this really useful function from Torch Vision called compose. Torch Vision transforms compose. They're a really useful way of transforming your inputs and your outputs, and become particularly useful when you do vision sort of work. So this class has been written in an entirely general way, so we can provide multiple target keys, so we can do multi-class and multi-label classification using this class. One other thing of note is that I'm not going to go too much into detail what compose does, but you can basically just daisy chain transformations together, and you just loop over your transformation. So it leads to a much more modular and clean code. I can see a lot of baffled looks on the audience. But if anything isn't clear, we can always go through it in more detail. So you might be asking, well, why? Oh, actually, no. Let's leave that to one side for now. But I'll go back to the simpler implementation. I just want you to be aware that if you want to write more general code, you can, and you provide these transformations which can be used like this. So in getItem, we apply all of our transformations to both the features and the targets. Anyway, I'll leave this to one side. You don't have to do anything, but you can modify. If you have a bit of time later on, you can go back to this exercise and see how you might do this in a more sort of general way. Okay, so let's go back to this function. I probably might get annoying. No, okay. So now that I've completed these two tasks here, we're now getting the data set in a format that we can deliver it to the model. So is everyone okay with that? Is everyone kind of up to speed with that? Let me know if not. Let's go through something again. So I'm using two features and I'm trying to predict my species class. Okay. So this is kind of hinting about what I was talking about, that we can apply transformations as arguments to the class. And it allows us to switch between training and validation transformations more easily. That's the fundamental point, that we don't want to apply the same transformations to our training data as we do to our validation data. We want to test or evaluate our model on as real world data as possible. We don't expect to have augmented the data in any way. So that's kind of the flexibility it gives us. It's a bit contrived as well, this model, because in reality, you will probably pre-process everything at the start because it's such a small data set. As you can see, I'm kind of converting everything into tensors on the fly. So whenever I access an element, I convert it into a tensor. I'll get rid of that so I don't want to cause any confusion. Okay, so the next, once we've completed these to-dos, the next step is to create our training set and our validation set. So it's basically the same as what we did before with this data set. I just want to call them appropriate names. So we have data set here, copy this code. Rename these things. For validation, some people have probably already done this, but the only difference is I'm going to call this train set and call this valid set. So if you look in this class, you'll see that depending on this train boolean here, which is passed when we instantiate the class, we get a different data set depending on whether it's 0 or 1. You can look and don't worry if you don't understand everything now, you can look at it later. But that's kind of the logic behind it. And I made a mistake, so I need to set that to false. So just to check, I can do for beats odds in train set print. I can be a bit fancier here and pass another iterable Oh yeah. Oh yeah, I need to provide zip for that. So I just get the first 5 examples. Just a bit of way to sanitize the output. Okay, let's move on. There's an optional exercise if you want to use this other more sophisticated class to do exactly the same thing. And all you need to do there is, well, all you need to do is it's not trivial, but you will provide this compose object to your transformations, and you can do exactly what we did in the previous exercise, but in a more kind of general way. You have to import this Penguins dataset class directly from the ML workshop. Don't do that now, because I don't want to corrupt your notebook, but we're going to move past this exercise, and if you're keen, you can have a go at that yourself. Okay, as I said, to train a model, we need a data set, we need our model, we need our loss function, and we need an optimizer. Another aspect of the data set is using a data loader, and Isaac's already introduced this this morning, but this is something that kind of can trip people up. It's part of writing idiomatic PyTorch. We don't actually iterate over the data set itself when we train it. The data loader gives us a few additional useful tools which you should not ignore. So we can set the mini batch size. We're going to train on batches of some specified size. We're going to shuffle the data during each epoch, or every time the model has seen the data, that is the entire data set at least once. We also have some for more sort of computationally demanding problems, we can do parallel loading. So I think I might have already given the answer to this, but does anyone have an idea of what we should think about when we choose a mini batch size?
Where it fits in your GPU RAM. Exactly,
yeah. That's performance wise, computational performance wise. We want it to be able to fit into the GPU memory. There are other things, maybe thinking back to so interestingly, I got this as an interview question many years ago, and I don't think I gave a very good answer. So I'm going to ask you. There might be another reason why we want to, instead of providing a single example to the model, why would we want to provide, say, 16 examples, 32 examples, or 64? Does anyone have any idea?
To have some kind of variance in the data.
Yes.
Else you won't learn of it.
Exactly. Yeah. So I think, as far as I understand it,
I also break the IID. You need to have the IID.
yes, exactly. So there are a few other things. So if you provide one example, you kind of get maximum variance. The kind of the gradient points in loads of random directions, and it can be quite unstable. If you provide a batch size, you get more stable gradients in the training process. But that's my kind of understanding of this. So a bit of a rule of thumb is that, as well as performance issues that was already raised with the GPU memory and etc., it also is a benefit to actually use a batch size. Why might you not want to put in a massive batch size when you're training one? What's the downside of that? Is there a downside?
It's
If you can fit it all onto your GPU, then why wouldn't you? I think is the kind of the approach.
It's quite confusing about the pushing everything. Having chunks helps.
Yeah, having chunks definitely helps. Yeah, there's another aspect, which is that there's a possibility for the model to overfit if you provide very large batch sizes. So it loses its ability to generalize unseen examples. So a rule of thumb is that you don't, given the size of your data set, you have to make some decisions about how big your batch size should be. I'm sure the rules of thumb are out there for this, but just be aware of that in the session. Okay, so I'm going to move on from task for part C and create some data loaders. So this is quite straightforward to do, but train loader equals data loader.
Could you scroll down a little bit more so that the
Oh, I'm really,
type in sort of more?
I'm really sorry. Yeah, can you see that? Okay,
Yeah.
cool. Well, actually, maybe you have a go at creating this, and we can come back in a minute or so. I'll just leave up the class information there to sort of give you some idea of what you might need to provide. Another aspect of this is that you can also do hyperparameter search through your batch size, and that's probably something that you can just brute force it. I'm sure there are more sophisticated techniques than this, but you can brute force it if you want to do a grid search over your batch size. Okay, is everyone okay with that? I'll just provide an implementation. It's not too complicated. But, formatting is all off. Select triple equals true. Batch size. You don't have to do this, but it's useful for you to do it. Another thing that I forgot to ask.
Same number. Sorry.
Sorry.
I chose the same number. Sorry.
Another thing that might be interesting to go over is why we even bother shuffling the data.
Your model might learn a temporal sequence that you don't want.
Yes, exactly. Yeah.
The order should not be there. Want the model to know that okay, this is how it's gonna come after this.
Yeah. So if you provide all positive examples of if you've got two class classification problem, you provide all positive examples first, and then just train on all negative examples. At the start, it's going to learn just to say yes to everything, and then when you go to the negative examples, it's going to say no. So you need to intersperse the rows of your data set. I see it as a bit of a like you're trying to tax a muscle. You're thinking about going to the gym or something. You want to be able to give it something that it hasn't not really used to yet, and keep it on its toes. That's kind of how I think about it. I think by default it's false, but let's just give this a go. Okay, and just for just a sanity check, I'm going to loop over
Like we'll talk.
sorry,
Talk.
yeah, a bit of a mind, a bit of a blank then. Train. Yeah, that's probably not I have. Well, I'm gonna just call size on this. So you can see that we've got we're iterating over batch sizes of size 16 as we specified there, and with two columns or two features, which is what we're using at the moment. It might be good, it might be bad. We'll see how it performs. Okay, is everyone okay? Okay, if I move on, tell me if I'm going too slowly or. Okay, so we're gonna have a go.
Question.
Yep.
Why does the last one have a different size to
because the data set doesn't divide evenly by 16, so you get like a remainder of 1. That can cause issues, and we'll talk about that in a bit if it arises. Okay, so we're basically going to define some linear layers and non-linear layer activation functions. When we do a linear, when we apply a linear layer, we're basically effectively doing this affine transformation. So W transpose, W being our matrix of weights or parameters multiplied by our input to the layer plus some bias to them. The bias kind of helps us to, well, we're going to be using it's used for lots of reasons, but the main advantage here is when we're applying nonlinearities to the model or within the model, the bias ensures that the activations on average will fire. So there are cases when if you apply a transformation without bias, it's just not going to lead to anything that will activate using your activation function of choice. So the bias helps you to kind of get back to a point where the node will actually fire. Okay, so first of all, we're just going to create don't copy what I'm going to do now, but I just want to demonstrate what a bad network looks like, and then I'll generalize it. Keep it a bit nice, so if I can remember how to do that. So, so what you see in a lot of codes is this kind of behavior where they've hard-coded linear layers. And then we pass the batch through this network. I think this is sort of what Isaac was describing this morning, where you're explicitly having to pass the output of one layer into the input of another layer. And then, so, one thing I haven't mentioned, I haven't introduced any of this at all, but we're subclassing this module class, and this defines, well, this provides you with all of the architectural components that you need for defining your network. So when you subclass, you obviously have to call the initialization routine of the parent class. So this is really bad. As I was saying, you've got hard-coded definitions of a linear layer. You've got repeated code. So every time you have to change something here, you have to change it here as well. This is not the approach that you follow. So a better way of doing it is to use something called sequential, which is what Isaac was talking about this morning. And normally what you do is define everything in the initialization in the constructor. So oops, that's right. Oops. So we're going to do self.forward. So you can type this if you want. And then we provide sequential. I need to import. And then we just define our network in like a sequence. We basically daisy chain everything together. So we'll call first of all, we'll call the linear as before. So that will have size in feats. And then some well, not random, but some choice of output dimension. This is a height parameter that you have to specify. We're going to pass that to a ReLU activation function, and then create another linear layer. So this is all kind of going over the fully connected linear layer. Apply ReLU again, not ReLUI, and then do a final linear layer. Which outputs the dimension of our out feeds will be 3 in this case. So there are 3 species. And the forward function becomes very simple. It's just a case of running self.forward on the batch.
Just missing a comma system. Just
Oh, yeah.
first linear layer.
I was just wondering about that because it wasn't.
Yeah, syntax.
It wasn't showing that I was using this value import. Thank you. Okay, so hopefully that works. So we can probably test this. So let's instantiate it. And provide the arguments to that. So a number of features, which I defined somewhere else. So I didn't. I think it's just length of features. Yeah. Features. And I apologize, I'm not providing doctrines and type hinting here, or type hinting in particular. Bad practice, it's just going to take longer to type. So, but bear in mind that it's good to adopt these kind of type hints. I'm going to just hard code that for now. So we expect we're passing out a number of features, which is 2, and we get 3 out. Okay, let's just create some input data. This is different, just to test that this works. And then we provide that to the model. What am I doing wrong? Okay. Yeah, so we pass 2 features. That's well, maybe it's better just be length of features. And we get our outputs. It's not critical to do this test. It's just if you want to see if it works, runs the forward pass, you can check it. So there's even more general ways of writing this this class, which I'm not going to go into, but often what a lot of people do is you can completely automate the definition of your model by providing suitable arguments into your class. So you can imagine that you can provide a list of your linear layer dimensions and the transforms that you want to do. So ReLU or leaky ReLU or sigmoid. And then you can just basically loop over all of those things and then pass that into this sequential. So you can make very easily create very general code use PyTorch. But I'm not going to show you that. This is enough for our purposes today.
Oops. So if I do not use sequential, but I just do sort of the
You have-
chain.
Yeah, you have to provide the outputs of one layer into the inputs
Yeah.
of another, and that is prone to error in terms of human error. Try to even though it kind of hides exactly what's going on, it's better to write less code than more. Okay.
Well, in defense of doing that, if you get into a mess because your tensor sizes don't line up or something, being able to step line by line through the debugger.
But that is true. But in theory, you shouldn't be able to ever get into that mess because
I managed it in the past.
Oh, have you? Okay. Okay, so I've just got like an optional task, but it might be of interest for you to see this here. Torch Vision.models. Torch Vision is basically a package that has grown out of PyTorch, but for vision applications. But really, a lot of the functionality there can be applied to most problems. It's kind of become greater than what it was originally intended through years of development. So anyway, this model you can import directly from Torch Vision. The ResNet 50 example, which is often used for image classification examples or anything like that. So I'll just show you what that looks like, or you can execute it yourself. But we basically are downloading the ResNet model, and we're specifying that it will be set up with the pre-trained weights. Might take a bit of time. Okay, so we can look at the architecture of the ResNet model. See that it's composed of various convolutional layers, batch norm, ReLU, max pool, etc., etc. We can also, well, that's the printing model, but we can also actually look at the parameters that we get. There's a lot of these, but maybe just of interest to see. This isn't important for the rest of the notebook, but it's just something to look at. I haven't really gone into activation functions too much. Isaac covered this morning. There are other activation functions that we can use that might be a bit more performant than ReLU. I think over time, the trends or the industry and research has kind of moved and is now adopting different ReLU or different activation functions depending on what literature says. It started out with like sigmoid functions, went to ReLU, now we're on like leaky ReLU, and there's probably some newer, fancier activation function that's meant to perform better. ReLU is fine for our task. In fact, one might even argue that defining a model for this task is complete overkill anyway. But it probably is. It's just that this is a good data set to demonstrate some of the key functionalities of PyTorch. Okay, so let's select a loss function. So we want to create a loss function that determines the error between our predictions and our targets. So I think that's what you do. Very simple task. And is there anything else I missed? Yes, and I suppose the key thing to note is that this outputs a scalar. So as regards the optimizer, we're going to use Adam, which is some variant on stochastic linear descent. If you look into the documentation, should move on to that. Well, yeah, it provides you with a helpful pseudocode for how this is all set up. It's what everyone seems to be using, or maybe people have moved on to something even more performant than this. But this paper has thousands of citations. It's probably got 20,000 or 30,000 citations now. I don't know. It's a slight slightly improved version of stochastic gradient descent in that you provide momentum, which I believe adapts to the learning rate. So traditionally you provide a learning rate and it's kind of fixed to the duration of training. This adapts with the during the training process. So again, this is quite simple to set up. We just do Adam. And then we need to provide the model.parameters. So this is what connects our optimizer to our model. And we'll talk a bit more about that in a bit. But we can provide a learning rate. The default value is 1 times 10 to the minus 3, which I'll provide anyway. Let's just see like a, oops. Okay, so now we have our data set, we have a data loader, we have a loss function, we have a model, and we have our optimization routine. The next bit is to write the training and validation loops. So this is kind of the meat of the kind of the day, and maybe it would be good to have a go at this yourselves. I provided some helpful comments here, but maybe if I give you like 10 minutes or so to play around with that, we're making quite good time. So hopefully we'll be able to get to a point where we're training a network by the end of the session. But yeah, have a go at based on everything you know. You can go and look at resources online. Try and implement this. See how far you get.
The scheduler with
Learning this.
learning rate schedule.
Or
I mean, you don't generally need because Adam sort of changes the learning rate.
I'm sure you could probably find you could probably override the default behavior,
Yeah, but I just think
but the defaults might be quite useful.
Yeah,
like,
yeah.
pretty good anyway.
Yeah.
Yeah, I don't have a good answer. There's a lot of text here that I provided. The key thing is that you probably noticed that we're just getting raw logits out of the network. Possibly not that useful in terms of interpretability, but that's kind of all we need to provide to our loss function. And I'll explain a bit more about that in a bit. Yeah, I'll just give you 10 minutes and then we'll come back and let's go over this. If anyone's having any difficulty, let me know. I'll tell. Okay, how's everyone getting on with that? Does anyone have anything that trains? Anyone has anything that loops over the data set? And okay, I'll have a go at doing it. I probably will encounter issues as well, so we can work through them together. So the first thing that we have to do is to set the model up for training. This is very important. It changes the behavior of certain layers in the model. We don't have any of these layers enabled yet, but we will do. The second thing of equal importance is zeroing the gradients. So optimizer dot zero grad. If you don't do this, then gradients just keep accumulating. the computed gradients just keep accumulating on each iteration, and this becomes this is completely unnecessary to do. So it's like performance trick. Oops, got some inputs. The second thing we do is run the forward model. So the output will be something called our predictions model on the batch. Okay. We then compute the loss, the cross entropy loss equals is this loss func. It's kind of idiomatic to put predictions first, but it doesn't really matter. Then we compute the gradients by calling this backward routine. So as Isaac introduced this morning, we're just computing the derivative of the loss function with respect to all of the gradients in our model. And we use backpropagation to do that. And then to the other equation that Isaac showed of subtracting from the current weight, we subtract the derivative of the weight with respect to the derivative of the loss with respect to the weight multiplied by the learning rate. This is done with the optimizer dot step. Okay, so that should run. We've got another routine in task 10 which loops over all of the epochs for you, with epochs set surprisingly low to 3, but we'll change that in a minute. We want to be able to record our loss and our accuracy, so I'm going to instantiate a metrics dictionary. Loss. See, that's how it works. So on each iteration, we the model sees a single batch, which I think we define to be 16 examples. Where to put this? Yeah, 16. Sorry for moving around too much. So I want to be able to append these to the to our metrics dictionary. So first of all, loss is quite straightforward. We append to the array, which is indexed by the string loss. And it's just a case of doing loss dot item. Item is a way of getting the type, the underlying type within the tensor out of the tensor. So in this case, it would be a scalar. So we have lists of scalars. Yeah. Is everyone okay with that? Yeah. Anyone not okay? Anyone confused? Anyone? Some help?
Loss and optimize. If we lost it backward, then I can optimize the step.
Yeah, that's a really good question. And it's not obvious. I think, in fact, there's a better description of this in these hidden cells. There you go. How does the loss know about the little parameters in the model? In summary, this is the kind of key line here. You're running a prediction over your batch, and when you run this prediction, you run the forward step, and you construct your computational graph. And surprisingly, this is done each time. So every time you do this loop, you have a whole new set of inputs, and you construct this computational graph every single time. And you can quite easily see how the predictions get past this kind of prediction tensor, which also has all of the functions kind of collected, in this forward pass is passed onto the loss function, the lost or backward. It kind of all flows where it flows down. Now, I was kind of preempting that question, and if you can do this anywhere, but well, you don't have to if you don't want to. But if you just import torch and then do actually no, probably from torch import ones, and then we do ones of 5. So we've got a 5-element vector within our tensor type. We can actually define requires grad equals true, and this tracks all of the operations that are applied to that type. So say I do ones times which I mean I have to do something a bit more advanced, but exp 2 times 5. Oh, it doesn't have it built in. Okay, let's ignore that for now. Once I oh, what's going on? What am I doing wrong?
Or using the function. You have a one-stop
Remember that
function.
signed it to tell it how many elements.
Oh, thank you. Yeah. Mhm. So this is an illustration of how PyTorch works under the hood, but you can see that we've got this multiplication backward within the gradient, and in a hand wavy way, this is tracking all of the mathematical operations that are applied to these objects. By default, when you call model requires grad will be set to true. So that's how you compute all of the computational graph that's being built. Okay, so that's a good question, thank you. So we also want to track the accuracy. So we've got our predictions, and we've got our targets. That operation will fail. Our predictions is a 3-element vector. So many people might think, well, you're just getting some random raw outputs out of your network. Maybe we want to get that in more of a human readable way, and you can with something called softmax. This basically gives you some kind of probability vector on your prediction. It's not necessary to do that for this example, because softmax is monotonic. You basically, if you call argmax on this, it should give you the same. It doesn't really matter ultimately. We get raw output out. That makes sense. If I explain that very well, but this gives us a Boolean tensor. We call float on that because we still have a tensor which has all of these additional functions that we can apply. One being float. We can also then apply the mean. And is that what I need, or do we need item? Yeah. So that's a bit of it's a long horrible line. I probably would be better off putting that into its own function, but for brevity purposes, it's quite easy just to put it there. So that will give me my accuracy on a batch level. So I average over each, there are 16 elements, and I get accuracy on that. But that's not all. That's not what we want. We want to get our metrics over the entire epoch. So we do a very quick dictionary comprehension to get this in a nicer format. So this is where I'm putting it. So just excuse these variable names as well. Yep. Okay, so this basically is that the item. Yeah. The items. I always forget that. And so when we iterate over dictionary to get the values out, we need to record the items on it. So basically, all this is doing, if I can just tab away for a second. So say we have loss. So say we have a dictionary of loss. 1, 2, 3, and accuracy. So accuracy. Accuracy. 0.1, 0.2, 0.3, 0.4. Let's see what's that. Then essentially all this is doing is it's key value for K. That's will fail. That's define mean. So all it's giving you is a single value of loss and a single value of accuracy for your training epoch. Okay. So if you go back to the cost entropy loss, you can see that in fact it does softmax already for us. It's basically a combination of log softmax followed by the negative log likelihood loss. So it's all done for you. So I'm basically delegating a lot of the heavy lifting to the PyTorch libraries. Okay, I need to actually just import the from NumPy import mean. This isn't very happy. I think it's configured by float family. You don't have to do that, it's just for type hinting purposes. Okay, does it given that, do people want to just have a very quick go at doing the validation loop as well? In fact, it's a lot simpler. Not just at the time. So in fact, there's only really 2 steps to do here. But maybe the most important thing to mention is that there are a few things that we should consider when running the validation loop. We don't need to track our gradients, so we can provide from Torch import no grad. It's a completely unnecessary thing to do when you're evaluating a model. We're not going to be backpropagating at any point, so we just set that. So we import this function. We can do that. We can use that function as a with block or something a bit more fancy as with Python decorators. If I can find at laptop. So at no grad will tell it that we don't need to track gradients. The important thing to do here is that we want to put it into evaluation mode. So model.eval. This is really important to do because we want to be able to take the statistics of the data set that we've learned from the from training and not compute any new statistics on the data set when evaluating. So this is a problem that's you can find a lot in academia where people have used the mean and standard deviation that they've learnt during training, and during evaluation they drink all of their statistics and it leads to anomalously good performance. That might not be immediately obvious because at the moment our network is very simple. We basically just have a series of linear layers followed by ReLU, linear, ReLU. But there are other layers which perform differently depending on whether you're running in evaluation mode or training mode. One of those is batch norm, and the other is the dropout layer. So I believe that the in evaluation mode, it turns the dropout mode off, as well as batch norm. We don't want to be learning the statistics of the validation data during evaluation. I think that's all explained in the notebook. Okay, so as before, all we really need to do is compute the predictions and brain, and also compute our loss. I don't know why I'm typing this because it's already up here. Okay, so we don't need to run the backward on the loss, or we don't need to set the gradients in the direction of C%. We can just copy all of the metrics code as well. Okay, so in theory, we should be in a position with 10 minutes to go to train our model and evaluate it. Oh, I forgot one thing. I also need to do the same thing with the turn of the validating epoch. Okay, is everyone happy with that? Okay, so we're just going to append these to a dictionary. Maybe I'll call it metrics again. Training metrics, valid metrics. Yeah, sorry, I have to concentrate for a bit. Yeah, so this should in theory track all of our training metrics, and I'll just check that trains. If it does, fingers crossed. Okay, it did something. Training metrics, so look at what it did. I'm just going to keep training it. Okay, so we've trained it. The accuracy is pretty poor. So what should we do? Should we increase? We'll increase the number of epochs. And I'll increase it to 100 epochs for now and see what happens. Is everyone training in it? Has everyone got to the point where they're training a model? And it's actually doing something?
It's doing something, but the loss and accuracy are not changing with each iteration.
Yeah, that's expected.
Oh.
Yeah. Well, I am getting some changes in the loss and the accuracy. So maybe you might have done something a bit. So you should get something where it's doing something, but it's not performing very well. We have 5 minutes to get this working.
Oh, maybe it's because I was so obviously containing the same list. And so I was seeing the first element of the list again and again and again. So I was doing something strange. Just indentation. It's too fast.
Yeah, this is the problem with Jupyter notebooks. So it's quite hard to track whether you've defined things previously as similar names or not. So let me open my pattern review. Jupyter does, if you're using VS Code, you do have this, which kind of helpfully defines what you've got set. Sometimes useful. My advice would be to clean all output, start again, and start. Anyway, so we have a model that's performing really badly. I'm kind of in two minds. If you're coming tomorrow, I'm hoping to start on a completely different notebook, and I can very briefly go over how to get this working well. We have an hour, or you can have a go at it yourself tonight. I can hint as to how this can be improved. One of the questions earlier was that we haven't, would you customarily normalize your data? The answer is yes. And as you can probably see, we haven't done any of that. So there's a very easy way of normalizing your data. Have a go at it and see how far you get before tomorrow. So are there any other questions? Or people very dissatisfied that my model? So my hint is that you can either normalize your data manually using a transform that we talked about earlier, or we can set some useful layers here to do it all for us. So have a go at that. And I'll go over it very briefly tomorrow. or if anyone has a go at doing that now, then tell me what accuracy you get, because you should be able to get up to 95% accuracy. It's a very simple data set. It doesn't need a very complicated model. There is just one bug there. Okay, if there are no more questions, we can end a bit earlier. Do a shock face.
We are predicting labels, right? Just
A single label, yeah,
a single label.
but multi-class single label.
Oh yeah, so in this case, we've got three kinds of penguin, so
Yeah.
I guess we're predicting like 0, 1, or 2.
Yeah.
So when would you instead use one-hot encoding, where you have like a kind of vector of
Yes.
zeros and ones?
I would suggest using one-hot encoding for multi-class, multi-label classification. You don't need it for here. In fact, it does lead to problems if you use one-hot encodings for multi-class, because it's helpful to work through the maths, but it leads to quite a subtle problem in terms of what you're actually optimizing. With one-hot, you're kind of assuming that everything's independent. Your classes aren't independent here.
I'm not following. Sorry.
Well, your classes are either one species of penguin.
Yeah.
We're not expecting those. We don't want to use one-hot with binary cross entropy, which is the approach that you might use. Sorry, Jack.
Because if you were one-hotting, your output could be like 0.5, 0.50,
Yes.
whereas like you can't have a
I think with
0.50 species of penguin.
yeah, if the standard way is, so I'm a bit shaky on this, but the standard way of doing this is if you use binary cross entropy with one-hot encodings, basically what you're telling the loss is that you want to force everything to 0. And that is I don't think it would affect this problem at all. In fact, I know it doesn't. You can do that, but you're trying to do an unnecessary optimization task. You don't need everything to go to 0. That is the negative class. You just need the positive class to be more positive than the rest of them.
But if we have like 100 or 1,000 categories, we'd never be able to predict an integer accurately. Like classification of like penguin variety number 237.
Yeah.
So then what we have to do is sort of one thing in a different
But-
kind of optimization.
We're doing that in this example. We have three different species of penguin. We're just going to output a vector of logits from the model.
Oh, sorry.
Yeah.
Right, I've lost track. Right.
So we are actually outputting a single,
Okay. Right.
sorry, a vector of outputs.
Right. Sorry, that's my misunderstanding.
Yeah, and then we do argmax of that. So we just get the maximum value of that list.
Our features is 3, right?
Yes. Yeah. So because we have 3 different
So
species.
just do soft max. So you get values that sort of the 1.
Yeah.
It will obviously have some classes at a higher probability.
Yep.
Then do cross cat will be possible.
So there's no point in doing softmax here because softmax is already built into cross entropy loss.
Oh yeah, yeah.
So yes, in practice, if you wanted to code all of this yourself, you would do softmax almost certainly. What you don't want to do is do softmax in your network and then do softmax again in the loss.
Yeah.
So don't do repeated applications of softmax. Okay, shall we leave it there? We can cover some of these things tomorrow as well. But yeah, thank you for listening.